Hi, Year 12. I'm just recording the CWR for week 7, term 4 on Young's modulus and factor of safety. Now, the first thing that I want to reinforce is, I'll get this pointer up, I can't, is how to work out the force required to punch a hole in a material. And then the second question that's generally asked is what force or what stress is in the actual punch when it's going through the material. So the first one here, what is the force required to punch the hole in the plate? And that's the answer there. And so this is number 1 here. So you write down your formula, and I've always asked you to put your data down here and make sure that you include the units there. And I've explained why you do that in an exam, because it does get you marks if you get the wrong answer here. So then we want to find the force required to punch the hole. So you transpose this equation. So force equals shear stress multiply the area of shear. Now, this is where you've got to know the difference. The area of shear is this perimeter multiplied by the thickness, because the punch doesn't cut the area, it cuts around the perimeter and then it goes through the thickness. And so the examiner will be looking at this. First thing they look at is to see what area you've used. So here we have the perimeter of the hole. So you've got 20 there, 20 there, so that's 40. Plus you've got half a circle there, half a circle there, and it's got to be the perimeter, so it's pi d. So we've got pi d plus 40, that gives you the perimeter of the hole, and 10 is the thickness. That tells you that it's 10 millimeters thick up there. And then you close the brackets, do it mathematically correct. It's always good that way. And then you multiply by 10 to the minus 6 to bring it to meters squared. And I always recommend you work that out numerically. And so that you've got the numerical value here. So you're not putting all of that into this equation over here, just putting that in. And so the shear strength of the metal is 400 megapascals, and I haven't put 10 to the 6 in there because it's cancelled by 10 to the minus 6. So it's 400 times 777, which is the area in square meters. And you've got 310.8 kilonewtons, which is equivalent to about 31 tons. And so you'd go and buy a air cylinder or a hydraulic cylinder, which is around about 40 or 50 ton or 400 kilonewton, so that you could punch the hole out. You know, the holes aren't drilled very much in industry now, because a normal circular hole has a volume of pi r squared times thickness, and the drill actually cuts out that whole volume, whereas a punch just cuts out around the perimeter and then through the thickness. Now, the next thing you've got to do is work out the factor of safety. So what's the factor of safety if the compressive proof stress of the punch material is 1760 megapascals? So that's the compressive stress or strength of the material that you actually go and buy for the punch. And so you've got to work out what the compressive stress is when you apply a force of 310.8 kilonewtons to the punch. And the reason why you've got to find the compressive stress there is because that's the working stress of the punch. And so you just work out what the area of the punch is. Now, we're working out the cross-sectional area here now. So it is 20 times 12 plus pi r squared. So we've got 20 times 12, which is a rectangular section, plus pi r squared. Now this is the cross-sectional area. Multiply by 10 to the minus 6, and it will give you the value in meters squared. And so you substitute that down here, and so you get the working stress of 880.2 megapascals. Now, if you have a look at the factor of safety on page 38, you'll see that the factor of safety for ductile materials is either the yield stress or proof stress over the working stress. And so we've got the compressive proof stress. So we've got proof stress over the working stress, where the proof stress equals 1760 megapascals, which is that down here. And the working stress, in other words, that's the stress that's on the punch as it's going through the metal, is 880.2 megapascals. And so you just substitute it here and you get a factor of safety of 2 for that. And it's really important for you to have a look at page 38 with factor of safety, and make sure that you know those two diagrams on page 34. The first one shows you a stress strain diagram with a definite yield. And notice that those diagrams that I've given you there are stress strain diagrams, but this one down here is a load strain diagram that we'll have a look at in a minute. Okay, so that should be okay now. Now, number 2, from the load strain graph of a pre-stressing tendon given below, determine the Young's modulus of the material. Now, let me explain what this graph is here. When they were building a shopping centre near our place, they had to use post-tensioning, pre-stressing, and this tendon here that you see here, they delivered the tendons in rolls. They were in coils, and that's why they have to have it as a cable, not as a solid material. And along with each coil of tendon material that came from Lysarts, when Lysarts were open in Newcastle, I think, they supplied the testing data of that coil of post-tensioning material, tendons. And BHP or Lysart, whoever it was, just do it as a load strain diagram. And so if you want to convert this to stress here, all you have to do is divide these values here by the nominal area. The nominal area is the area of this cable, and it doesn't take into account the voids in it. And so you've got to, because that's 143 millimeters squared, you've got to multiply that by 10 to the minus 6 to work out the cross-sectional area in meters squared. So that's one thing you've got to do. Now down here, you probably already know that you can't put percentages into equations, because a percentage is a ratio. Per means divide, so 8.8% is 0.8 divided by 100. And so to get the numerical value, you've got to divide 0.8 by 100, and that will give you 0.008 strain. And remember, there's no units for strain because it's a ratio. So that's just explaining these axes here. And as I said, BHP supply this data with each of the coils of the tendon material, so that if anything goes wrong with the post-tensioning, they know that it wasn't the fault of the tendons failing. And so the first thing I want to do is just explain Young's modulus, and then I'll explain proof stress. Young's modulus is, modulus just means a number, and Young developed this, and it's the modulus of stiffness. And see the slope of this straight line section, that indicates how stiff the material is. Now, this material has got a Young's modulus of around about 180, 890, and that's about consistent with steel. And the slope of this straight line section is, you know, slope is gradient, and gradient is opposite over adjacent. And so it's the tangent of that line there. And so Young's modulus, the formula for Young's modulus is stress, which is opposite, and you can't use load, you've got to convert these values to stress. So it's opposite, which is stress, over strain there. And you can't use percentages. You've got to divide that by 100. And so that's what Young's modulus is. It's an indication of the stiffness of the material. Now, the stiffest material on planet Earth is diamond, and that's got a Young's modulus of 1220 gigapascals. Now, don't forget, giga is 10 to the 9 and mega is 10 to the 6. And so diamond is 1220, and steel is around about 180 to 210. I think stainless steel is around about 180. Glass, because you can change the properties of glass. Glass has only got a stiffness of 50 to 90 gigapascals. Lead, you know, lead isn't very stiff, and that's only 14. Aluminium is about 70 gigapascals. And the new wonder material, which is called graphene, which is going to revolutionize batteries and just structures in the future. It's a two-dimensional hexagonal structure, which has got extreme strength, and it's got a Young's modulus of 1,000 gigapascals. And so that's why that's going to be a material of the future when they can manufacture it reasonably cheaply, which will happen. So that's Young's modulus. And so remember, you can't just use that value there. You can't say it's 189 kilonewtons over 0.7. You can select anywhere along this straight line to get Young's modulus. You can't say 189 kilonewtons over 0.7. It's got to be 189 times 10 cubed divided by 143 times 10 to the 6 divided by 0.007. So let's have a look at it up here. So here you have Young's modulus. You've got to know that Young's modulus is stress over strain. They'll give you that in your formula sheet, but it's really important, I think, for you to learn it. Where the stress equals 189. See, I've selected this point here because it's right on that 0.7 down here. So, and you go across here and you see that the load or the force is 189 kilonewtons. So I've got 189 times 10 cubed divided by 143 times 10 to the minus 6. There's a nominal area, 143 times 10 to the minus 6. And that gives you 1321 megapascals. So that's the stress. And so we've worked out the stress there, 1321 megapascals, which is fairly high stress, divided by 0.007, not 0.7. There, it's got to be worked out numerically. And you get 188.8 gigapascals, which is what we've got there. So that's Young's modulus. Now, the next thing I've got to explain is proof stress. Now, if you have a look at page 34, see that top diagram there? That's called a stress strain diagram that has a definite yield. Now, when I used to do tensile testing of wire material and bolt material, it always amazed me that when you reach the end of the straight line section, which is the limit of proportionality, with these metals that have a definite yield, you could see the metal still stretching, but the load going down. And that's because the atoms move into new sites. And so it doesn't need that much energy. And so the load goes down, and that's called the upper and lower yield. Now, that only happens on around about 15% of metals. The other 85% have the diagram on the bottom there. And so engineers want to know how much yield this metal can go before it starts damaging the design. And so they've worked out, and I'll just select. They've worked out that if you draw, if you draw a line from 0.2% strain parallel to the straight line section, and where it hits the graph, you just draw a horizontal line across there, and you get what the force is at that point, and then you divide that by the cross-sectional area, which is 143.2. Yeah, so we've got it's about 249 there. So we've got 249. The proof stress is that should be 249 there. So I've got only 24. It should be 249. I've got it right here. Divided by that, and that will give you what the proof stress is, 1741. Okay, so that's how you get the proof stress. And it's analogous to the yield stress in ductile materials. And this is called progressive yield. Last question, stress and strain at the proportional limit. Now, the proportional limit is where the graph deviates from the straight line. And the examiners give you a fair bit of leeway there because different people select different points for the proportional limit. But we've got the proportional limit there. You can see the graph is deviating from the straight line. So you go across here and you get 216 kilonewtons. So the proportional limit is 216 times cube load over that. And so you get the proportional limit of 1510 megapascals. And then you just drop a perpendicular down there, and you see that it is at 0.8% strain, which I've got there. Okay, I hope you understand all that. And